Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and we will continue our discussion on the finite differences method. And what we're going to discuss in this lecture is the implementation of what we call an implicit FDM method. So essentially one in which the solution at the current time value or the next time level is not just simply dependent on values at the previous times level, which are explicitly known. Rather, the solution or the temperature values or whatever the field variable is at the current or next time level are all interrelated. They're also related to the solution at the previous time level, but they're also related to solutions at other nodes in the current time level, which leads to what we call an implicit scheme. Basically, you will have to solve for things simultaneously. It leads to a simultaneous system of equations. Now, this is obviously more cumbersome than the explicit scheme. And algorithmically, you would have to solve a system of equations. There's added complications. There's added overhead. It will be a lot slower. But there's one major advantage that we'll discuss at the end of this process. So let's go. Modeling methods in ME. And what we'll discuss today is an implicit FDM formulation. So let's start with the governing equation, and we'll discuss this with a simple governing equation. Again, the diffusion equation in space and time. So one-dimensional diffusion equation. Linear, no generation. Again, this can be generalized and extended as complicated as we want, but we'll do the formulation this way. Now we're going to discretize time as n times delta t, such that n goes from 0 to n, and delta t is equal to some final value of time divided by the number of time steps. And time and space xi goes as I delta x. So we have a number of grid points where I goes from 0 to I. So we have I plus 1 nodes. And delta x is simply L divided by I, the length of the domain in the x direction divided by I. Then position the governing equation at xi comma tn, right? So this will be the second t dx squared at xi tn is equal to 1 over alpha dt dt xi tn. And what we're going to do is use a central differencing approximation, CDA, of the TDX, or the second derivative of time with respect to x squared, and a backward differencing approximation of t, of dt dt. And to make things a little bit clearer, I am going to, instead of positioning at tn, I'm going to position at tn plus 1. Okay? This will make things a little bit more simple to understand. It's the same. Instead of relating n to n minus 1, we'll relate n plus 1 to n. All right. So if we use a central differencing approximation of this space derivative, we'll have t at I plus 1 at n plus 1 minus 2 t at I at n plus 1. Remember that this is position at n plus 1 plus t at I minus 1 n plus 1 divided by delta x squared. And this is equal to 1 over alpha. And if we use a backward differencing approximation, this will be ti at n plus 1 minus ti at n over delta t. So, as you can see, we cannot solve for ti at n plus 1 as a function of everything on the right-hand side that we know at the previous times level. So what's going to end up happening is that on the left-hand side, we're going to have the Fourier number times ti plus 1 n plus 1 plus 2 Fourier number plus 1 times ti at n, plus 1, minus the Fourier number times ti minus 1 at n plus 1. And on the right hand side, we simply have ti at n. So as you can see, we send the delta t and the alpha to the left hand side, flip the signs, send the ti n plus 1 to the left hand side, and ended up with this expression. Such that the Fourier number, as we know, is defined as alpha delta t over delta x squared. All right, and this right here is an implicit scheme, implicit FDM scheme, valid at interior nodes. So at I equal 1 to I minus 1. It's not valid at the end nodes, right? And it's called implicit because we cannot explicitly know what happens to ti as a function of stuff that happened in the previous time level. We would have to know what happens on the nodes right next to it too. So essentially, if we were to graphically illustrate this, and again, let's just put this here. If we were to graphically illustrate this, and we'll denote time and the y-axis and space and the x-axis. Again, assuming that this is, let's say that this is Tn and this is Tn plus 1, and this is I equals 0, I equal 1, then we have I minus 1, I, and I plus 1. And then we have here I equal I minus 1. And here we have I equal big I. And this is the domain in this direction. So let's see. And then at t n plus 1, at the next time level, we have exactly the same domain in space, the same nodal distribution. But now, the solution at these three nodes depend on themselves and depend on the solution at node ij, at node I, at the previous time level. All right? So we're going to know this one, and this one. It will depend on themselves and the one at the previous time level. So this scheme leads to a system of simultaneous equations when the expression above is evaluated at I equals 1 to I minus 1. So let's see that. So basically, if you take this and evaluate at I equal 1, right, what will happen is like, well, I'm going to position the ti minus 1 here, the ti plus 1 here. So I'm just going to flip this too to help visualize this better. So at I equal 1, we have f0, t0 at n plus 1, plus 2 f0 plus 1, t1 at n plus 1, minus f0, t2 at n plus 1 is equal to t1 at n, which we know. The right hand side we know. So this is at I equal 1. Right? So at I equal 2, we can do do it right here. This will be minus f0 t1 at n plus 1 plus 2 f0 plus 1 t2 at n plus 1 minus f0 t3 at n plus 1. And that's equal to t2 at n, which we know. And then at I equals I minus 1, we have minus f0 ti minus 2 n plus 1 plus 2 f0 plus 1 ti minus 1 minus f0 ti n plus 1 is equal to ti minus 1 at n, which we know. So everything from the previous time step n, we know. In addition, at nodes I equals 0 and I equal I, so the n nodes, we can formulate similar expressions for the boundary conditions as we did for the explicit scheme. In fact, nothing changes in regards to formulating the boundary conditions, first kind, second kind, or third kind. So what would happen is that this leading to a system of equation A that contains the temperature at the next time level is equal to the temperature, or we're going to call it the vector B because it's not only the temperature, right? Some of the vector B will contain the temperatures, right? But some of it might contain the first element, and the last element might contain information about the boundary conditions, right? So the size of the system is I plus 1, comma I plus 1. The size of this vector is I plus 1, comma 1. And the size of this vector is I plus 1, comma 1. So this is a square system of equations. There's I minus 1 equations here, but then you have an additional equation for the first boundary condition and an additional equation for the last boundary condition, right? So you have I plus 1 equations with I plus 1 unknowns, which are the temperatures at all the I plus 1 nodes. So this is a linear system of equations. This is a linear system of simultaneous I plus 1 equations. It may be solved using any algebraic solution method, such as, for example, Gaussian elimination, LU decomposition, SV decomposition, singular value decomposition. These are all well-known techniques. You can ask MathCAD or MATLAB to solve the system for you. That's pretty easy to do. You can use also iterative techniques like Gauss-Seidel or conjugate gradient, or by conjugate gradient or GMBrush, all kinds of different methods of solving square systems of equations, linear system of equations. And one thing to note is that it doesn't matter what happens, right? It doesn't matter how you formulate this. This matrix A doesn't change. It's not a function of time because it contains information about the Fourier number, and the Fourier number doesn't change as long as you don't change the nodal distribution, the delta x, and the boundary condition distribution doesn't change in time. The not the boundary condition value, but the boundary condition type doesn't change in time, the matrix A doesn't change. So notice that the coefficient matrix A does not change along the time progression or iterations. It stays the same. So basically, if we just try to solve the system as t at n plus 1, it's just basically the inverse of a to the minus 1 times b, which is information of the field at time level n, which includes the temperature and the boundary condition information. The inversion, if you opt to do it by inverting the matrix A, the inversion, which inverting a matrix is it's a computational costly process, but the inversion of A only needs to be performed once. There are other alternatives. You can find the LU factors of A and then just keep those LU factors, lower and upper triangular factors. Is another way of doing this. Another way of accelerating this process, the point I want to make is that if your system of equations will look like this, and your system of equations will need to be solved at every value of n. So at every value of n, you'll need to solve an I plus 1 system of equations, which is very costly. So this is going to be significantly slower than the explicit scheme. However, there are things that you can do to accelerate the process. One of them is like, well, you can invert the matrix once and use that inverse forever. But also you can realize, the matrix A is mostly filled with zeros. So it's highly sparse. Or sparse in this case. So notice that the equation, each equation only for node number 1 only depends on the node right to the left and the node right to the right. Equation node number 2 only depends on node 1 and node 3. So basically this equation is A is tridiagonal. Tridiagonal. What this means is that A, if you were to plot it as a matrix, remember its size, it has I plus 1 columns and I plus 1 rows, or I plus 1 rows and I plus 1 columns, that's the right way of saying it, would have a 0, 0, a 0, 1, and then a bunch of zeros here. Then we'll have a 1, 0, a 1, 1, and a 1, 2. Then it will have 0, a 2, 1, a 2, 2, and a 2, 3, and then a bunch of zeros, and leading to zeros, a bunch of zeros, a I plus 1, comma I, and a I plus 1, comma I plus 1. So basically, this matrix has a diagonal, it has a super diagonal, and it has a subdiagonal. Only the diagonal right above and the diagonal right below. And everything else is filled with zeros, everywhere else. So these can be solved very efficiently. Tridiagonals, systems of equations can be solved very efficiently by techniques such as the, for example, Thomas algorithm. This is an algorithm that basically addresses matrices that are like that. And also, it can be efficiently stored in memory because you don't need to store all the I plus 1 times I plus 1 elements of the matrix. You only need to store the diagonal, super diagonal, and the subdiagonal. That might not seem like a lot, but remember when we do problems are in 3 dimensions and have millions of nodes, try to store a 1,000,000 by 1,000,000 matrix, and you will soon find out that you don't have enough memory to do that. 1,000,000 times 1,000,000 is essentially 1,000,000,000,000. So that's a terabyte of memory just to store. A terabyte times, well, each element, if you do it in double precision, is 8 bytes. So it's 8 terabytes of memory just to store a matrix that is 1,000,000 by 1,000,000. If you have 1,000,000 nodes in a 3-dimensional problem. So sometimes you cannot afford to do that. Now, implicit scheme are far more computationally expensive than explicit schemes, and they yield the same accuracy. So there's nothing different that we did here when we took the differential equation and evaluate the differential equation or discretize the differential equation using a central differencing approximation in space and a backward differencing approximation in time. So this is order delta x squared accurate, which is the same as before. And this is order delta t accurate, which is the same as if you did forward differencing approximation. So we didn't alter the accuracy of the scheme. So what is the gain if we're losing in computational efficiency? It's basically the only advantage of implicit schemes is that they are unconditionally stable. They don't suffer from stability issues. You don't have to worry about the size of the Fourier number, right? So if you do a Fourier analysis, if you put in a wave in the grid distribution and let it evolve in time, any errors in the wave, actually any peaks and troughs in the wave would actually compress to zero, will diffuse to zero, regardless of what the Fourier number is. Alpha delta t over delta x squared can be as high as needed. So you don't have to compress the size of delta t to unreasonably small value to make this Fourier number small. So you can actually make delta x small, right? Which is what you want. You want to make delta x small, so your space discretization is small, so you get a good resolution and you get a good error, or small error. And then the delta t doesn't have to be quadratically smaller to maintain the value of the Fourier number. So you can afford to do larger time steps with very small grid sizes. So FDM schemes can also be formulated as combinations or mixes between explicit and implicit, and these are the so-called Crank-Nicolson schemes to yield accuracy and stability. So you can compromise on one end and gain on the other, and so on and so forth. In addition, explicit, this is something that I mentioned last class, and implicit schemes can be used to address steady state problems by formulating them as what we call pseudo transient one. So we basically put in a diffusive term on the right hand side, an accumulation term, dt dt, come up with an alpha that doesn't exist, something that we can control, and advancing it in time until it reaches an asymptotic solution, that is steady state. Okay, so if you're confronted with having to solve a steady state problem and having to use an FDM approach, you could formulate it as a steady problem. It's just that you're going to end up with a much different formulation that basically presents a system of equations, a simultaneous system of equations, where all nodes are related to all nodes, in a sense, and then you'll have to solve that large system of equations. Rather, you can formulate it as an explicit, an implicit, or a combination of the two, and that's it. This may come in handy for some applications. All right, so let's work on an example of this implicit approach. So for an implicit FDM example, we are going to solve the same problem that we solved originally for the explicit formulation 2 lectures ago. So we have a one-dimensional transient problem that's no generation, homogeneous. We have an initial condition, t of x, 0 is equal to t0 of x, whatever that is. And boundary conditions, on the left we have q of at x equals 0 equal to 0, so that means that dt dx at x equals 0 is equal to 0. So it's insulated on the left. And on the right, we have q at x equal L is h times t at x equal L minus t infinity. And so that means that dt dx at x equal L plus h over k times t at x equal L is equal to h over k times t infinity. Okay, and we are going to make t infinity equal 0 for this particular example. And then we had formulated this, we had actually found the analytical solution for this problem in terms of eigenfunctions, right? And the eigenfunctions are going to be the cosine of lambda n x. This combination of boundary conditions lead to a cosine eigenfunction. And the eigenvalues are an implicit relationship that has to do with h over k and the tangent of lambda n L. And then the constants of integration have to do with the integration of the initial condition times the eigenfunctions, and the solutions in terms of an infinite power series. Okay, we did this before 2 lectures ago, the same analytical solution. We're just going to basically compare and see what happens to the numerical solution when we implement this implicit approach. So let's go to MathCAD. I've already done that for you. So the implicit FDM example, we're going to set L as 1. We're going to set in SI units, that will be 1 meter. K, we're going to set as 1. And in SI units, that would be watts per meter Kelvin. And diffusivity alpha is going to be 10 to the minus 3. That will be meters squared per second. Again, we're going to set the initial temperature to be this parabolic distribution that is 0 at the ends and 100 in the middle at L over 2. We're going to set the flux on the left to be equal to 0. We're going to set the film coefficient to be 1. And in SI units, that will be watts per meter square Kelvin. And we're going to set the temperature on the right-hand side, the convective temperature to be 0. This is a algorithm that we've implemented before to find the eigenvalues. So basically the eigenvalues obey the relationship that the tangent of lambda L is equal to h over lambda. And so we're basically going to iterate every pi over L and see when these actually matches, and the left-hand side matches the right-hand side. And at that point, we name a new eigenvalue. And then we're going to store 100 of them in this array lambda. We did this before. Then we are going to calculate the constants of integration, 100 of them to be precise, and the constant of integration is equal to the inverse of the norm, which comes from the table, right, times the integral from 0 to L of the initial condition times the eigenfunction. And the solution, the analytical solution, is an infinite series. We're truncating the series at 100 terms. Is constants of integration times the eigenfunction times e to the minus alpha lambda square times time. We're going to evaluate this for 1,000 seconds. And we're going to discretize space with 11 from 0 to 10 nodes. Each node is separated by delta x of 0.1. And we discretize space as xi equals to I times delta x. Likewise, we discretize time using 100 time steps. So each time step is of size 10 seconds. And so time is discretized as n times delta t. The Fourier number then, alpha delta t over delta x squared, notice is equal to 1. So if we had formulated this as an explicit scheme, it would be unstable. We've already proven that if the Fourier number is larger than 0.5, the explicit scheme, which is very simple to implement and very efficient computationally, will just give you erroneous solution because it would just diverge to infinity. So it will be unstable. And the Biot number is the relationship of the convective coefficient to the conduction is 0.1 in this case. So the elements of the matrix A, let's look at the interior elements of the matrix A from node 1 to node I minus 1, so the interior nodes. So at every one of those rows, the column I minus 1 has minus the Fourier number. The column I, so the diagonal element, is 2 Fourier number plus 1. And the super diagonal, the column I plus 1, is minus the Fourier number. On node number 0, we have a second kind boundary condition. So we are basically relating Q as delta T over delta I. The T dx is equal to Q divided by K. So that means that relates the temperature at node I with the temperature at node I plus 1, the node right next to it. So the temperature minus the temperature at the next node will be Q delta X divided by K. And on the right-hand side, we have a boundary condition implemented in terms of convection. So basically, the node on the right-hand side, at I equal to capital I, is 1 plus the Biot number. That's the coefficient that multiplies the temperature at that node. And the coefficient that multiplies the temperature at the node right to the left is minus 1. You can formulate this. This is the same expressions that we formulated before. That will yield a matrix. If we print A, actually let's just go a couple rows below. As you can see, the matrix A has a diagonal, a super diagonal, and a subdiagonal. Everything else is 0. This matrix is very easy to invert, and we only need to invert it once. So we just basically say C is the inverse of A. So if we print C, C is going to be this matrix. which is not as sparse as the matrix A because it's not necessarily tridiagonal. Even though the matrix A is tridiagonal, this has a lot more elements. But basically, if we say how much is C times A, we should get the identity matrix, because the inverse of A times A is 1. It's the identity matrix, and that's indeed what we get. The algorithm is very simple. So first of all, we fill the initial condition, right? At all the nodes, the temperature at all the nodes and time equals 0 is T0 of xi at all the nodes. And then we loop over all the time steps from n equals 0 to n minus 1. We implement the right-hand side. We find what the right-hand side vector b is for the interior nodes. It's the temperature at the previous time level, level n. On the first node of the right-hand side vector b is delta x over k times q0. That's the boundary condition on the left-hand side, q0. And the boundary condition, or the vector b at the right-hand side, is given by the boundary condition at time at the last node, and that will be the BO number times the temperature infinity, or the convective temperature. So essentially, the temperature at the next time level will be the inverse of matrix A, which we already place into C, so we don't have to calculate the inverse at every time step, times the vector B. The only thing that changes as time evolves is the vector B. And at the end of the day, we'll have a temperature distribution. We call it TIMP for implicit, that has as many rows as the number of nodes and as many columns as the number of time steps. So if we say print here what T implicit is, as you can see, we have 11 rows. That is the number of nodes. At time equals 0, notice that the T0 is the temperature at time equals 0 is given by that quadratic relationship. We impose a quadratic temperature distribution. And then as time evolves, that actually tries to settle and diffuse. And we did this for 100 time steps, or 101 time steps. And that's the distribution of temperature over 11 nodes over time. So, as we did for the explicit scheme, I want to see the temperature distribution at time equals 0, and that's perfect between analytical and numerical, because that's imposed. At 1% of the evolved time, so we said that the final time was 1,000 seconds, so this will be 10 seconds. This is what the analytical solution is, the red line, and the dots are the implicit solution, the numerical one. Again, there's some error in between the two. That's expected because the nodal distribution is very coarse. But as you can see, even though, and this is what happens after 100 time steps, and this is what happens after, this is what happens after 100 seconds, and this is what happens after 1,000 seconds. So as you can see, there's an error between the numerical and the exact solution due to the coarse distribution of nodes. So the grid size is a little bit too long. But even though there is a very large Fourier number in this case, the Fourier number is 1, which will result in an unstable solution that would actually be completely useless for an explicit scheme. In the implicit scheme, we get an answer. All right. Now we can actually afford to make that delta, that Fourier number, even larger. So say, for example, we want to, instead of using 10 nodes, we're going to use 20 nodes. Right? Notice the Fourier number is 4 now, which would be even more unstable. So if we use 20 nodes, we should get a better representation in space. And that's indeed what happens. See? In space, at 1% of the time, there's still a little error there at the end because of the boundary conditions, but we're getting a much better solution. And if we change that to, say, 50 nodes, now the delta x will be 0.02, leading to a Fourier number of 25, which is very, very high. But again, this is an implicit scheme, and it will not care. This is what happens. This is the temperature distribution after 10 seconds, the temperature distribution after 100 seconds, and the temperature distribution after 1,000 seconds. It hasn't reached steady state because in this problem, steady state is 0. So the whole temperature profile will go down to 0. So as you can see, implicit scheme is a little bit more convoluted to formulate, but it actually yields stable solutions even for very, very large values of the Fourier number. So that's what I wanted to convey today, the idea of implicit schemes for the finite difference approximation of at least diffusion problems. You can do the same with wave-like problems or any type of boundary differential equation or partial differential equation. You can approach this way in terms of initial value problems. Again, you can use it to approximate the solution of steady problems by just creating a fake time distribution and evolving it in time up until the solution doesn't change anymore. In this case, the solution will settle to, if we make, for example, let's make this 1,000 times steps. So we'll go to a final, actually, let's go to a final time of 10,000 seconds. 10,000 seconds and do 1,000 times steps. And this is a solution after 100 seconds, after 1,000 seconds, and after 10,000 seconds, the solution has gone down all the way to 0. So we can find out that the asymptotic solution is basically 0. And that makes sense because this problem is homogeneous on the boundary conditions and on the governing equation. So there's nothing to bring it out of 0 in steady state. All right, so that's all I wanted to show today. And thank you for your attention, and I'll see you next time.